Hi guys, back to mathematics, Fundamental Theorem of Calculus Part 2. So what we did talk about last week was how to find the antiderivative, and we used the power rule, constant multiple of power, and sum and difference. So we learned how to find the antiderivative. That was our thing. We also learned how to find the derivatives. So the general form of antiderivative is given a special name and notation. So we are going to use something that will look a little bit different, and it's called the indefinite integral of our function f of x, and it's defined by, and now here's the integral notation. So it looks like this. And we say that the integral of the f of x is going to be f of x, so that's what we were using before, plus some constant c. So again, my f of x, but written with the capital letter, is the antiderivative of the f of x, and c is any constant. Keep in mind the notation. You can do what you did, well, at least what I remember doing in elementary school. You would do the rows of the same new letters. Still remember that. Anyway, so that's our new notation. Keep that in mind. You will see this in a second. We'll start by solving this very long word problem. So I will post my notes as well, so you can have it in front of you. Students in technology class are participating in an egg drop competition. Each team must build a protective device that will keep an egg from cracking after a 30-foot drop, and the instantaneous velocity of an egg can be defined as. So that is the important information. This is our formula, where t is given in seconds and velocity is measured in feet per second. So the first thing that we want to do is we want to find the position of position function s of t of a dropped egg. So, well, let's hope I will have enough room here on my paper. The first thing that I want to do is I want to find my s of t. And I know that s of t is going to be, here's I am using my new notation, the integral of the v of t function. And now the notation I need to use is dt. Well, I had this, I did not mention this, I will put my paper in a second, because this was f of x, dx, that's important notation. Here my function is in terms of time, so dt, whatever letter is your variable, you'll put d of that letter. All right, so that's the first thing. So what I need to find is I need to find the integral, and my v of t function is defined as negative 32t. And again, the notation dt. You will see when you will be in calculus class, you will get used to this. This is just an introduction, and it will feel a little bit odd at the beginning. All right, so now the next thing, we will have to think of our formula. What was the formula that will help me find the antiderivative, or what's the formula that will integrate something that looks like this? So this is going to be, well, think about this for a second, negative 32 t to the power of, well, 32 t to the power of 1 plus 1. I'm just writing all my work, and I'm going to divide it by 1 plus 1. And again, I need to remember about constant c. And of course, I do want to simplify this. And because I do want to simplify this, I will say that, well, I have 32, negative 32 divided by 2, that's negative 16. Negative 16 t to the power of 2. And again, I do need to remember about my constant. So now, because this is a nice particular situation, I am able to find my constant, and I will find my constant by substituting the 30 feet that I had given, and I am going to substitute that for the initial height. So if I say that 30 is equivalent to negative 16, and again, because I want the initial height, I will put it as 0, and then I will square that, and I will add my c. This is giving me 0, so c is equivalent to 30. And notice what that helped me do is that helped me to find the formula, and the formula is going to be s of t is equivalent to negative 16t squared plus 30. All right, the second part of this problem, which I am going to write on the side here, is to find how long will it take for the egg to hit the ground. So if I want to figure that out, I will solve for t when s of t is equivalent to 0. All right, so now let's see. 0 is equivalent to negative 16t squared. I'm using my equation from here, plus 30. Well, there's a couple ways of solving this. What I am going to do is, well, I am tempted just to move this on the other side. So 16t squared is equal to 30, divided by 16. Well, this is a pretty messy way of doing this, but that's okay. Divide by 16, and t squared is going to be equal to 1.875. And if I square root that, we would have to remember that we would get a positive and negative number. However, we are only interested in the positive number, and I did that. Square root is equal to 1.369. So the egg will hit the ground in about 1.37 seconds. Very interesting. Look at that. You were able to use calculus to figure out problem like that. All right, let's see what else we can do with that. So finally, we have our fundamental theorem of calculus, and we have a definition of that. And if the f of x, and notice this is is an antiderivative of the continuous function f of x, then antiderivative of f of x in some interval from a to b is going to be equivalent to the antiderivative of f of x in this point minus this point. Okay, you will see in a second when we look at the example, it is going to be clear. Again, fundamental theorem of calculus. In calculus class, you will be using it all the time. What it helps you do, or one of the very, very important use of it, is when you have a function that is given, the function needs to be continuous, you can graph that function and you can find the area under the curve. And you will see, we'll just do some basic example here, and this is going to clarify everything. So again, keep in mind, I will try to keep my definition there, but if I don't have room, I will move my paper so you guys keep it in front of you. So I want to use the fundamental theorem of calculus to find the area under the region between the graph of each function and the x-axis. So this is my function, and this is the interval. Well, if I wanted to graph something that looks like that, and again, I want you to keep in mind, I only care about 1, 2, 3. So I will only care about what is going to happen between those two numbers. And so now, how is the 4x to the power of 3 looks like? Well, you could use a graphing calculator, but I know that for 0, 0, I am at 0. For 1, I would be at 4 x. So yeah, so 1, 2, 3, 4. For 2, I would be at, well, it grows pretty quick. for 1, 2, 3, 4, 4 to the power of 3, 4 times 4, 16, 64 times 4, well, really large number. All right, but I do see that this is happening. And basically what I am looking for is I am looking for the area. I'm looking for this area, and notice that you have never done anything like this before, because this is a curve. So we could not say, well, this is a trapezoid or whatever other figure you could create, because what happens is this is a curve. So the fundamental theorem of calculus and the antiderivatives will help you to find something that looks like this. All right, so the very first thing that we need to do is we need to find the antiderivative of 4x to the power of 3. Again, notation dx, we need to make sure we write that down. Notice I did not write the intervals yet. We will do this in just 1 second. So now, what is the antiderivative of 4x to the power of 3? I'm going to use the formula, and again, for those that are just starting this, I am going to write exactly what the formula tells me to do. So I will have 4x to the power of 3 plus 1, and I am going to divide it by 3 plus 1. I know that I have to add my constant c, and after simplifying, this is 4, so this simplifies, so I get x to the power of 4 plus c. So notice that our previous notation, that would be the f, the capital F of x, that would be our antiderivative. So now, what do I need to do with this? I need to make sure that I calculated this on the interval from 1 to 3 of the original, so 4x to the power of 3 dx. And now we always start with the top number, so you are plugging it into your antiderivative. Okay, so we will have 3 to the power of 4 plus c, 3 to the power of 4 3 to the power of 4 plus c, and then I am going to put this in parentheses just for fun of this, just so this is a proper notation, minus, and in place of x I am going to plug in 1 to the power of 4 plus c. So notice what I am doing is I am using this, and I am plugging my interval restriction in it. We always start with the 3 first, the 1, the bottom line, the bottom number is second, and we always put the negative sign in between them. All right, 3 to the power of 4, 3 to the power of 4 is 81, and then I have 81 plus c, but I do see the plus c minus c is going to cancel out, so I have 81 minus 1, and 81 minus 1 is equivalent to 80. And notice that because this is the area, I am going to say that this is unit squared. I don't know what unit. Well, were we given any units? Not really, so I am just going to say that it's unit squared because this is the area. Pretty fascinating. Again, for the first time here, you were able to find the area under the curve. And again, that's calculus for you. We will do one more example. I do realize that those notes are quite long, so they will take you a little bit of time just to do notes. I will give you a few examples that will be just like this, so you can practice. And then tomorrow or the next lesson is going to be again still on the fundamental theorem of calculus and practicing all that together. All right, so one more example. Notice I still want to use the fundamental theorem of calculus to find the area under now this curve. Notice this is a quadratic equation. This is going to be a parabola, and I want to look at this from 0 to 4, and the area is between that parabola that we will draw in a second, and the x-axis. That was our problem. So well, if I just quickly plug in 0, I am going to get so if x is equal to 0, y is equal to 6, and then the parabola, well, I don't think that there is a nice I'm trying to figure out what the zeros are, but it really, well, I am not going to graph it perfectly. It looks like this, and if you graph it on a graphing calculator, you are going to see that 4 is here. So the x-intercept is past 4. So what we are going to look for is this area between 0 and 4. So again, it's a nice area under the curve, and let's see what happens. So first we are going to find the antiderivative. Oops, that's not what I meant to say. Negative x squared plus 4x plus 6, and then I am going to put my dx. Just to be a little bit more proper, I am going to put this in parentheses. And I do know that I need to do this on the interval from 0 to 4, but I'm going to take care of this after. So the first thing is let's integrate that. Let's see what this is equivalent to. So the first part is going to give me negative 1 over 3 x to the power of 3. Again, if you need to write this out, please do so. So that is going to give me 2x squared. And then I am going to have 6x. I always check, whenever I write this, well, if I put the 3 in front, that is going to give me this. If I put 2, that's fine. And then I know that I have the constant c. All right, so I simplified this. Now I am going to evaluate this, and I am going to evaluate this from 0 to 4. And again, I'm going to put my original x squared plus 4x plus 6. And I have the x. And this is going to be equal to. So now, in place of x everywhere, I need to start by putting the 4. So negative 1/3, so I can put this on one fraction line. So I am going to have 4 to the power of 3 divided by 3 plus 2 times 4 squared. Oops, I don't know why I was trying to do the fraction. Plus 6 times 4. And then I have my c minus, again, I have a negative, and now I will be inputting 0, which is going to be extremely convenient. So I will have 0 to the power of 3 over 3 plus 2 times 0 to the power of 2 plus 6 times 0 plus c. Well, again, convenient because all this is going to be 0, this is going to be c, which the c's are going to cancel out. Now, I did use the calculator to do that. 4 to the power of 3 divided by 3, and that's a negative number, 34.67. And then for the second part is the 0, that's what we decided. 34.67 is this entire thing. So what we did find is that the area under the graph on the interval is 34.67 units squared. Again, how nice it is to find something like this, completely different. We, as I did mention before, we did skip a section where you would build a rectangle under the curve and then find the limit and approximate the area. That is something that you will definitely do one day when you are in a calculus class, but then you will know how to find that area algebraically. All right, we'll do a little bit more tomorrow.